recording, and then I'm going to explain what we're doing today. So basically, I'm supposed to explain percentages today. I'm supposed to explain percentages, and the first thing I'd like to explain would be ppm, parts per million. That's what it's supposed to represent. It's supposed to mean parts per million. Parts per million. It is exactly like it sounds, but the formula is not really what it's the formula for this is just equal to the mass of the solvent. Mass of the solvent over the mass of a solution. And this is times 10 to the power of 6. Basically, because, and the key to understand here is that solvent is just basically like, if it's easier to just give you an example. So like, say these black dots right here, that's like the worst drawing I ever made. I think you can see these black dots. Let's say these black dots are like pepper, and let's say I have like a container of water. This water would be the solute, and this water would be the solute. Solute in this case. Solute, and then this would be the solvent in this case. And then solvent, and then the solution would be when you put put this pepper into the water. When you put it into here and you say you stir it, and then wrong thing. Say you stir it. You stir and mix, stir them together. What happens after that is that's basically the solution. That's basically just the solution. And it's pretty simple once you reach that point. It's literally just the solution. Stir them. It's just the solution, which is basically just stirring them together. And basically all this is doing is, I don't think, okay, yeah, I've explained. And then the solution is equal to them, not string together, it's stir together. Stir them together, and that's basically in this case. So basically all this is, for solution, if you want a better definition, is that this is just, because look, mass never changes. So when you put solvent of solute, you're just like adding masses together. So all it is just mass of solvent plus mass of solute. Mass of solvent plus mass of solute. And basically the general definition of this solvent and solute after my example is that solvent is basically just the physical object mixed in. Oops. Yeah. It's just the physical object mixed in, and then the solute is basically just like the liquid it's mixed into. It's always a liquid mixed into. Remember that. Now this is basically how I would define it, and that's basically ppm. The reason why I multiply by 10 to the power of 6 is that this is just a percentage at its current state. Mass of solvent over mass of solution is just like a fraction or a percentage. So you have to multiply by 10 to the power of 6 to get the per million part you see here. And that's basically the ppm. This is pretty much all you need to know. And I think James and Raymond already explained yesterday. I'm just gonna take a screenshot of this in case you guys ever want to refer to this. I might post this, I might not. It all depends. So after we've explained, Density Lab is not the hardest event out there. There are many harder events, but the hardest part in terms of my perspective
It's conversions. See, it's conversions. There's many different conversions in density lab. Convergence. This comes in many areas in conversions for density lab, because as you probably already know, density lab is just mass over volume, and there's many ways to do this. You can do grams per liter, grams per centimeter cubed, grams per milliliter. There's many different ways you can express this. I'm not saying these are all the. Okay, I should actually rephrase this. I'm not saying all of these are the same values. I'm just saying these are all examples of what mass per volume. These are all examples. They're not actually actually equal to each other. I'm just telling you these are examples of mass per volume. And you probably realize this by now, that not all of these are going to be the same same density. These are all representing density. So in the case of, I know it's pretty easy when you're working with just saying like the top or bottom number, but what happens when you put them together? Well, the key thing I've learned is that grams per centimeter cubed, let's say this is like 1 gram per centimeter cubed. In terms of kg, that would be 1,000 grams per centimeter cubed, kg per meter cubed. This is just something to keep in mind. I'll tell you exactly how to convert this, but this is something to keep in mind for the most part. This is something to keep in mind for the most part. This is just something you need to keep in mind, because this is the most heavily used conversion I've ever seen and you probably need to understand this. And this is basically density. Now, and there's many other forms, because 1 gram per centimeter cubed is also equal to 1 gram per milliliter. 1 gram per milliliter. In terms of volume, centimeter cubed and milliliters are the same. So what happens when what if this is if I erased everything on this side, and I said, okay, so what if I turn this to milliliters? What happens? So what needs to be first understood here? I'll just erase all this. So what needs to be first understood here is that you need to first understand actually, I'll just grab a table. I'll just grab a table. What is this conversion table? I'll just grab a table, because it's like way harder to try and explain it while I could just grab a table. Give me a sec. I have to find it. Yeah, I'm not getting anywhere. I'm sorry, I'm a little bit unprepared. This table. This is a table you must know. This is a table that you must know. No matter what, you must always understand this table. I'll put on the whiteboard if you're interested, or this table must be understood. It's very important to understand this table, this conversion table, because in the end, everything is based off of this. You can see that you can basically see how you would denote this. Always memorize it by exponential notation. I wouldn't care about the meaning. I would only memorize the symbol, prefix, and exponential notation. And basically, you would understand this as, say like I had 1 milliliter, milliliter of some random thing. I'm not gonna give you an example. That would be equal to 1 times 10 to the power of negative 3. That's how I would do it. That's how I would express it as, because this is very useful. So because say now we're trying to convert grams to so with this, let's try to see what 1,000 kilograms, because a lot of these questions in density lab, they can be conversions. They can purely be conversions, and you're expected to know this. Kilograms per meter cubed. How would you convert that to grams per meter cubed? Grams per centimeter cubed, I mean. How would you do this? The key to understand is that meters cubed, okay, so we can start at the top. we know that all this is 1,000 times 1,000 grams. That's all it is. 1,000 times 1,000 grams. That's easy to understand. Now what about the meter cube part? Well, what does that work? Well, in a meter, there's 100, but it's not like just 100 on the bottom. It's going to be 100 times 100 times 100, because if we think about this, each meter is equal to each meter. When we look at this, it doesn't really state, it doesn't call it that. Okay, but like in a meter, there's 100 centimeters. So basically, you just, when it means that cube, you're literally taking that literally. As basically another way to restate this is that it's 1 meter cubed, 1 centimeter cubed. That's another way to restate it if you want. And that's basically just 100 times 100 times 100. And all you're doing is just multiplying all these numbers out. So like this is supposed to be a million, but I can just do 1 times 10 to the power 6 G divided by grams divided by 1 million. 1 times 10 to the power 6 centimeter cubed. And that is why when we convert to 1,000 kilograms per meter cubed to grams per centimeter cubed, you get this 1 gram per centimeter cube. Do you see what I've done here? Do you see what I've done here? Okay. We cannot multiply this. It's not an equation we're trying to do. We cannot multiply. What we're trying to do is we're literally just trying to convert each of these values to the centimeter, to the respective values, and this is the most common thing. Now the reason why the grams and why I specifically state 1,000 kg per meter cubed and gram per centimeter cubed, 1 gram per centimeter or something gram per centimeter cubed, is because the key to know is that water density, you need to always memorize this because all experiments use water. In your binder, you can include all the densities, but the most important one that you should always have in your head is 1,000 kg and 1 gram per centimeter cube. These are the two different forms of water, and you just need to memorize that this is water's density. You just need to know this. It's a given to know this, because if you don't know this, your math will be like 10 times slower. Other liquid densities or material densities, either they'll give it to you or you have it in your binder. You need to have that in your binder. The key to know is that this is the only thing that you should just have in your head. And I'm just going to take, if you guys want me to take do you want me to give you more examples about how to convert, or do you guys understand it already? You guys want to give you guys more examples how to convert? Oh, so more examples? Okay, I only see one person. A little more, please. Okay. So I already took a screenshot to help it out. Let me really quickly. I'm just gonna make sure I'm actually recording. So like, oops, the people who aren't on here, I just gotta make sure I'm recording. Okay, I'm recording right now. So basically, let's give a random value. I'll give you okay, let's say I have one. Let's just choose the most random value one. I have 3,000 grams over per 1 liter. Let's say this is the density they ask you to convert. 3,000 grams per liter. Well, this is actually a lot easier because unlike centimeter cube, where you see unlike centimeter cube or meter, unlike meter cube or like per se centimeter cube, where you can see this cube, because this cube means that what it's truly representing is that there's mm. And there's something I have to mention. Whenever you try to calculate something, always display the units on. Whilst it's always a good idea. So like we're trying to just convert this to like let's try converting this to kg per meter cube. So right away we should understand that to get to kg for the top part, we just need to do times 10 to the power its true value is this. Remember if you look at our diagram right here, if you can see this, I think you guys should be able to see this diagram. You guys can see this diagram? I'll just copy and paste this because it seems like we need this diagram like almost every time. But you guys should already know, you guys should understand that the kilo is 10 to the power of 3. So when we're looking at grams to convert, we're doing 10 to the power of negative 3. I know it should I'm pretty sure most of you guys know that 1 kg is equal to 1,000 grams. But it's just the way you understand this is by using multiplying by tens. Because if you think about this, another way to see this is that I think you guys, it's 3 to the power of 10 to the power of 3. That's the same thing as 3,000. But the key to understand is that I'm pretty sure you guys understand that when you multiply exponents, you add them up. And that's why in this case, when you add them up, this just turns to 0. That's why you don't need to worry about that. That's another way to look at it. And I would suggest looking at it this way because it makes math easier and simplification easier, and it's wholeheartedly just easier. It's not 0. It's not 0. It's 10 to the power of, it's just 1. It's equal to 1 because 10 to the power of 0 is just 1. And then 1 liter, we need to understand that 1 liter, I believe, is 1,000 milliliters. Or I'm supposed to do it 1 times 10 to the power of 3 milliliters. Because if you look at our diagram right here, milli is 10 to the power of negative 3. So when we say milliliters, we mean 10 to the power of negative 3. Or in this case, it's 10 to the power of 3 because milliliters is that basically means that milliliters is 10 to 1. It basically means that 1 milliliter is equal to 10 to the power of negative 3 liters. That is what the exponent is meaning right now. That is what the exponent is meaning. So that means that in 1 mil, that means that in the reverse way to think about this is that times 10 to the power of negative 3, 10 to the power of 3 is equal to 1 liter. This is the true way to think about it because in a milliliter, there's 10, basically that's how to think about it in terms of value-wise. But we do it this way to find milliliter. Because as I explained before, another common concept I tried to explain before, but I don't think I went too in deep, was that milliliter is equal to centimeter cubed. That is the milliliter is equal to centimeter cubed. That is something to understand. Milliliter is equal to centimeter cubed. Now, I am pretty sure James and Raymond went into sig figs with you guys and how it was an extremely boring lesson they told me. Sig figs, all you need to know is that when you're doing any calculations, it's the simplest way to do sig figs. It's just to make a simple reminder. Any calculations, leave your answer with the number of sig figs What this basically means is in any calculation, whenever you multiply, there's always these different numbers. Like when you do 3 times 8 times 5, you know that each of these are one significant figures. If you just want to choose whichever number has the lowest significant figure, the number of the lowest significant figure is the number of significant figures you will see in your answer. That's the simplest way to think about significant figures. You don't need to know any other thing. The only other thing to know is that there are exceptions to sig figs. Sig figs do have exceptions. They do have exceptions and they do not apply everywhere. Say you know that there's 4 physical apples. You can count 4 apples. If you can count the 4 apples, you cannot do significant figures when you're doing 4 times 3 apples. You cannot just say that you cannot round that to 10. It's still 12 because you can physically count them. You know they're there. That's not like calculations. You'll understand that later. Milliliter is equal to centimeter cubed. So going back to this example, we just want to get to milliliters to find kg per meter cubed. So if I did the math here after I've done the conversion, that's 3 divided by. Wait a sec. Oh yeah, that's true. This thing is extremely not dense at all. Milliliters. It's grams per milliliter. So now that we already know this, do not. That basically what this means. Wait, no, it's kg. Wait a sec. Yeah, I was right. 3 kg per milliliters. 3 kg per 10 to the power of 3 milliliters. And with this knowledge, you just want to convert milliliters to meter cube, and that's possible because we know that milliliters is just centimeter cube. So with that, we can just draw. I'm gonna do this in a different color because maybe you guys might be confused at this point. We can turn this to 3 kg because we want to find kg per meter cube. We can turn this to 10 to the power of 3 centimeter cubed. And with that knowledge, remember what I've explained before. Centimeter cubed is just 1 centimeter times 1 centimeter times 1 centimeter. That's the key to understand. So in terms of meters, you can think of this. You can think of this as 10 to the power of negative 2 meters times 10 to the power of negative 2 meters times 10 to the power of negative 2 meters. That's another way to think of this. Each of these are in meters format. I didn't write that down. Meters format. Each of these are in meters format. I forgot to write that down, but like you can. Oops. But basically, this is what it is. 1 centimeter by 1 centimeter by 1 centimeter is just 10 to the power of negative 2 meters times 10 by negative 2. Because 1 centimeter, if you look at this chart, is just 10 to the power of negative 2 meters right here. 10 to the power of negative 2 meters. So that's all it's getting represented here. So then we can think of this as when you it's equivalent to 3 kg. I mean, the more you do this, the more in habit you understand all this. 3 kg divided by 10 cubed. And 10 cubed centimeter cubed, which means all we're doing is that 10 cubed to negative 2. Yeah. Wait a sec. I need to rephrase this one. So basically, when you look at this, all this is basically we're just doing 10 to the power of 3 times 10 to the power of negative 2. And I don't wanna I will this time, but like you understand that this is just cubed. But like for visual purposes, I won't do it cubed. I'll just do it non-cubed just for visual purposes. I think that's it, right? Okay, so 10 to the power of 3 times 10 to the power of negative 2. Wait, did I do something wrong? Maybe. I did do something wrong. It's a lot easier if I... Wait a sec. I think it's just... Wait, I think I may have done something wrong. I need to like see something. Oh, okay, I see. Now, my original thinking is right. So basically what we have to do here is that now we know 10 cubed. We're just doing this to the power of negative 2, I believe. Wait a sec. I feel like I'm doing something wrong because the correct answer, okay, I feel like I'm doing this the longer method, but the correct answer is that we should have taken a shortcut because this is actually quite a slow method and I wouldn't advise this. But the correct method is there's a way faster method to do all this. We're just coming because we know that 1 liter is equal. Because we know that 1 liter is just equal to 1 times 10 to the power of 3 milliliters. It's easier to just leave this as grams per centimeter cubed. It's easier to just leave this It's easier to just do it as this, because once you see this, you understand that it's just 3,000 grams divided by 1,000 milliliters. And to see this, you just cross out the zeros, and then you understand that this is just 3 grams per milliliter, or 3 grams per centimeter cubed. And I've already told you the shortcut conversion, but the shortcut conversion basically leads you with 3,000 kg per meter cubed. That was supposed to be the correct way to do it, but I took the slower method. This is the faster method to do it. The other method, it's a lot. I wouldn't advise that because it takes too long. Just use this shorter method, as you've seen here. That's basically the method I would advise. The other one, that one I realized it would take too long. So just use this method. So that's that. Do you guys need another example after this? Because I'm pretty sure I've explained this okay. Do you guys want another example? Oops, wrong. Do you guys want another example? Do you guys want another example? Anyone else? There's like 7 other people. Okay, sure. I understand. So no one else wants this. So once we've done this, I think. Oops, wrong ruler button. You guys can. I might take a screenshot of this if you guys want. This is a really useful thing I found out of like a textbook I pirated, but like it's perfectly fine if you just this thing is like a pretty good thing. I would recommend to have like that in your binder if you wanted to. Now, what else did you want me to explain, James? This is it. The only other thing that you might be asked to find is Wait, no, you wouldn't be asked to find anything else. What else? This is literally what James wanted me to do. He wanted me to explain conversion percentages with you. Well, if this much time left and me realizing we need...
Howard,
Yeah?
you can continue with gas laws.
Okay, sure. So, I'm pretty sure James taught this formula because if this is the most basic formula I've ever seen. PV equals to nRT. What this basically means is that T represents temperature in kelvins. I'm pretty sure everyone probably got them bored of this, but I need to repeat this. Kelvin temperature. This is supposed to be R, represents a constant. This is a constant. The constant changes depending on the. This is the constant dependent on the gas used and volume used. This is basically it. So the one, yeah, basically this is it. And you would have these in the formula. This is just volume. Volume is actually volume. As I've explained before, it can be different, but you would always like to convert this to your to the one you know, because I think there's many different, like if I search up an example of like gas law constants, because there's many different constants I could choose from. There's many different constants, which is why you should, like, it's just so many, like, okay, like I'm copying this image on here. Look, there's this many there's this many constants out there. Like, just look at this. You can choose any of these constants you want. Any of these constants would do you the trick. Any of these constants. The one that, and then this is supposed to be, I should explain all this, but basically this is pressure, and it's not gas use. Wait, why did I say gas use? It's not gas use, pressure use. It's pressure use. It's not gas use. It's pressure use. I was being really dumb. It's pressure use, not gas use, but it's pressure use. This is supposed to be in pressure. Pressure can pretty much be anything in this. Can pretty much be anything. It can be there's different ones. ATM, torr, well, there's a lot. There's atmospheric pressure, there's bar, there's ATM, there's Pascal, not ATM, torr, Pascal, bar. There's many different pressures you can use. Volume, there's many different volumes you can use. And then N represents moles. I'll explain this very briefly, but moles, an example of this is that moles is equivalent to 6.022 times 10 to the power of, this would be way too long to write, so it's 6.022 times 10 to the power of 23 atoms. 10 to the power of 23 atoms. This is the correct number. Moles, and basically what this represents is supposed to be it's supposed to be, basically it just represents you see the atomic mass, it's basically just 1/12 the mass of a carbon atom. Basically when you see like that atomic the atomic mass at like the bottom of a periodic table, like say if I brought up a periodic table, like this is just connected. I'll explain this just very briefly because most wouldn't even, where is it? Oh no, I know where to go to. You go to ptable.com. So if you go to, say if you go to here, what a nice table, right? So basically you see like the number on the bottom. If I go to carbon, it's 12.01111. It's very good number, but basically it's just, I think that's atomic mass. I'm not being dumb, right? Oops, wrong thing. Oops, what did I even go to? So atomic mass is just equal to, atomic mass, I was right. So it's just atomic mass on the bottom, and the atomic mass is just actually the number of protons. Number of protons plus the number of protons. This is a brief the number of, this is sometimes on the test, so that's why I want to go into detail this. Number of protons plus number of electrons. And you may be wondering like, why is this number as you've seen here in the P table? Why is the number always in like different? Because not number, you put less electrons. I explained this wrong. Neutrons. But basically the issue is that there's different types. There's different like different atoms, because there's different atoms because they can have it's the brief way to put it is that they can have an imbalance, they can have different number of neutrons or protons, they can just have a different number because it can still be the same atom. It's just atoms are decided by the electrons mostly, and the neutrons and protons they can change, and like eventually all the number of atomic mass represents is the average of the natural atoms that occur, average of the natural atoms that you can like find with the protons and neutrons, because there's like sometimes they get to a certain point they become imbalanced, and this is just all it is. Atomic mass is just like 1/12 carbon atom, 1/12 carbon atom atomic mass. You don't need to go too deep into this, but basically moles is just like, what moles are usually used for is that moles, so like say I've had like a can't think of anything. Oh, so say I have like a 1 gram of what is this, phosphate? I don't really, okay, yes, it actually doesn't matter. 1 gram of like wait, not 1 gram, this would be a little bit too simple if I did that. 12 grams of like we're gonna let's say H or whatever, it doesn't really matter because it's just the atomic mass that matters. So all of this is just, you're just multiplying this to find the number of atoms is our goal. You just gotta multiply this by 1 mole. I always write the units if you see mine. It's just, or not equal to, times 6 times okay, I'm too lazy, times this number. This is another part of density lab they might test you on, and it's usually those questions times this number of atoms divided by 1 mole, because it's in 1 mole. Remember, you can interchange these for numerator and denominator because they should be equal, but the key to understand is that you need to put it, this is just one way to find the number of atoms. If this was not an atom and a molecule, that would be a completely different story, and you would need this periodic table. If you were to take anything but like say because the atomic mass actually there's a couple. What basically you understand is that the atoms, when they're in atoms, you can just pretty much do it like this. 12 grams divided by 1 gram or 1 mole per gram. That's basically all you need to do if it's just an atom. If it's like say a molecule, I don't really think I should go into too much detail. But say I have like H2O. Basically, what you would do is that you would find the atomic mass of H. That is wait a sec. I think I did this just a bit wrong. Let me check up on something, and then let me check up on something just to make sure I did this right, because I took notes on density lab like last year, so I do remember how to do this if I remember this correctly. Let me check my notes real quickly. Oh yeah, I forgot. So basically it's not 1 gram. It's based on, you need to know the atomic table. So if H, the only reason why it was 1 gram in this case, I forgot, is because H is, you see this atomic mass right here? Say like I go to H, you see the atomic mass right here? Do you see H's atomic mass 1.008? It's just 1 gram, and that's literally how you do it. But if it was like a different molecule, like say let's say this is like carbon. Let's say this is carbon. We find carbon and 12.01111, and we just do 12. And then okay, let's choose a different number then, because you get the point though. You're supposed to put 12. You're supposed to put 12 if this was supposed to be like a different atom basically. And in terms of molecules, what you do is that, look, there's H2O is just meaning that 2 times H, so it's just 2 times 11, 2 times 1, not 11, plus whatever O is. So if I look at O is supposedly 16, 2 times 1 plus 16, and 2 times 1 plus 16 means that there's 18 grams. So then if this was H2O, you would just put 18 grams on the bottom and then put H2O. And that's basically how you find the number of atoms. This is a very common question that they think is very difficult, but it's very easy to know if you have a periodic table, because okay, most likely, you know how most of these values are pretty close to like okay, so most of these values, you know how like most of them, not all of them, are like close to like a whole number, like 78.971. Some of them aren't, so you won't do it like that. But if most of them are like near a whole number, you can just use the whole number value, like oxygen. But like, you get my point basically, and that's like a very simple explanation. But this is just a very expanded form of what the application of moles is. You might experience it, you might not. It all depends. But basically, what this is called the ideal gas law. I'm pretty sure 10 out of 10 you guys got a James explanation about that. And the key to understand for moles is that moles is just moles. Okay, it's just the value. It's just that many atoms. Okay, so moles in this case, if you, I'm not going to show to derive it, but basically, we got the ideal gas law. This is the ideal gas law. And one of the favorite things that I like to do to memorize the other gas laws is to make this big ass triangle and call this B, C, G, P, V, T. And what this basically means, this is a very good way to memorize how to memorize the laws. So this is G represents Gay Lussac. Do not make fun of his name. He's I did make fun of him, but like yeah, Gay Lussac. This is Boyle's. This is the different laws. Just I know it, but I'm gonna explain to you guys by telling you your trick at the same time. I use this trick. Samuel used the trick. Everyone pretty much uses this trick. Boyle's law, Gay-Lussac's law, and then this is supposed to be Charles' law. You can. It's pretty easy. You'll get the hang of it. It's pretty easy to memorize. Charles' law. So you pretty much know that, Boyle, B for Boyle, Gay, you can pretty much remember that, and C is Charles. So basically, how to memorize like the different gas laws and who belongs to which is that, say you have the formula PV, all you have to do is cover up, say you want to find Boyle's law, all you have to do to find Boyle's law is just cover up the T, and then you have, I don't know how to, Explain. Okay, no, screw this. I'll screw this. Say I cover up the T. Say I cover up the T. Say I cover up. I want to find Boyle's law. All I have to do is cover up the B, and then I have Boyle's law, PV. Say I want to find Gay-Lussac's law. All I have to do is cover up the V, and I find Gay-Lussac's law, P over T. You get it? And then if I want to find Charles' law, I just gotta cover up P, and that's V over T. Do you guys get what I'm saying? Like how to do this trick I've just told you guys? Do you guys get this trick? Okay, it's very simple. It's very good. Memorize this because I have it. I 100% memorize this. And then just to like this. Okay, this wasn't a really good way to do this, but like I don't even know how to turn this. How did I even turn? Okay, who cares? We can leave that standing there. So you can turn. So basically, Gay-Lussac's law is just a representation of Basically, Gay-Lussac's law is just V1. If you know the V1 over T1 is equal to V2 over T2. That is, my friends, that is my Gay-Lussac's law. Gay-Lussac's law basically just means that if I have a volume of an object and I have a okay, all of these temperatures on Kelvin, you can memorize this. Kelvin is equal to 273.15 plus Celsius. Whatever the Celsius temperature is, you just add this number to it, okay? I believe for Fahrenheit, it's like 9 divided by... Okay, you might need to know this. I've experienced this somewhat. It's just 9 over 5 plus 32. To get Fahrenheit, it's just equals F. And then F is equal to this. Or if you want to know, sometimes they ask you temperature conversions. This is just like a thing to keep in mind. And then it's just okay. Then Celsius is equal to F minus 32 times 5 over 9. This is just the things you memorize. But your goal is to get this K. Once you get K, all you have to do is that temperature and K. Basically, this law represents Gay-Lussac's law. Just represents that. Oh, if my original volume is this, my original temperature is this, and I change my volume inside that. It's changed my volume and changed my temperature. The ratios between these two will always be the same. You can see it. The ratio of this over this, that's how you can find the answer pretty much. So if you know the original volume of something, you know the original volume T, and then somehow when it's warmed up, when there's like a temperature change, or like there's a volume change, and it turns something else, all you have to do is just change it to, you already know the volume change, you already know the volume change, you already know original volume, you already know T. If you know these values, you can find the missing. That's basically what this law represents. And then PV is equal 1, PV1 is equal to P2 V2, and basically all the application of this would be that my original pressure, my original volume. This is not actually a ratio. This is the exact opposite. What happens is that if the pressure increases, so like say like my original volume is this, my original pressure is this. If my pressure increases, my volume needs to go down. That's just the logic to have when doing questions. Or you can think of this as that, oh, if I know my original pressure, I know my original volume, and like I know the change in pressure or the change in volume, I can know the other value because the law is right here. This is whatever changes, like the change in pressure, change in volume, you should know what the answer is. And it's this itself also shows that, say like my volume increases, my temperature increases in the terms of Gay-Lussac's law. In terms of Boyle's law, what this means is that, oh, if my volume increases, then my pressure goes down. Or if my pressure increases, my volume goes down. That's just something to keep in mind when answering questions, because some questions do ask logic-based questions like that. But this is just like to keep it. This is just how to find the formula. And if you already see like the pattern that's like going on. Wait, this isn't Gay-Lussac's law. I forgot. This isn't Gay-Lussac's law. I accidentally flipped this. This isn't Gay-Lussac's law. This is supposed to be Charles' law. Sorry about that. This is Charles' law, and then this is supposed to be this last law is Gay-Lussac's law. The Gay-Lussac's law is P over T, P1 over T1. And if you know the drill already, you probably already know. Oh yeah, it's gonna be that ratio I was talking about. Pretty much, yeah. Same thing here. Same thing with the volume temperature. My pressure goes up, my temperature goes up, and basically that's all this represents. And you pretty much understand this, okay? Do you guys understand this? I'm pretty sure James already explained this to you yesterday. Yeah, James. I know you spotted my mistake, James. I know you spotted my mistake because I just realized like when I was doing this, like something happened. But this, okay, I'm just gonna continue this black to the G in case you guys ever get confused. I'll redirect the arrows so like in case you guys might have been confused. And then this is basically it, and you can see everything here. And that's basically the simple explanation. If I give you any problem, you should be able to answer. Now this is like this is the most common question. These like Boyle's Gay-Lussac's law. Memorize the triangle I gave you guys. You guys can access later in the recording. The recording will be in 4K, so you don't need to worry about that. Eventually in 4K. So basically what happens in PV goes NRT is that what you want to know is that basically the equation, you pretty much, if there's a missing value, all you have to do is figure out, oh, pressure is this, volume is this, I know R, I know T, I can find moles now if they want moles. The same thing happens from something else happens. That's pretty much all there is to it. There's also a formula to find the moles, to shortcut in case they want moles. There's actually a formula. I must grab that formula because I myself forgot that. I could derive that, but that'll take like some time. And personally, searching it up would be like 10 times easier. Density dot random. Okay, so let's see if I can find this. See, look, this triangle is talking to. I have it right here. I'll explain to you some other logic later, but like that's just it. That's the stuff I'll tell you guys for now. Wait a sec. How do you do it? I'm being really dumb here. Don't blame me. This is it. Wait. Yeah, this is it. So the better basically it's equal to molar mass. Molar mass. They should give you it. They should give you this. If they don't give you molar mass, I'm pretty stumped if they don't give you, I'm pretty stumped. But I believe this is just constant times temperature divided by pressure times volume. I'm pretty sure this is it. Wait, is this right, James? I'm pretty sure this is it. You guys know this? No, wait. Oh man. Okay, I'll just assume I'll actually derive this then, because it seems. Oh no, it's not it. That's not it. You know what moles. You know what moles is. But n is just equal to all it is just you can already see from this equation. It's just PV over RT. I'm being really dumb right here. You already know moles. That's not the key point. The key I wanted to tell you about was molar mass, not moles. Molar mass is supposed to be equal to N times PV, N times, wait, a sec. Yeah, it's supposed to be N times over, it's supposed, wait, I'm feeling really dumb right here. I've done this before though. Yeah, RT over PV. This is very similar equation. You can see how similar they are. But the key to understand this is that molar mass is grams per liter. This is moles itself, I believe, is just wait, no, that's not wrong. Molar. This is grams per mole. While molar mass is just grams. It's just grams, and basically all you're doing is that you're reversing this, Because what happens is that now that you know the constant r and the constant t, what happens is that it just goes backwards, and this should be the equation, I believe. I'm sorry if my teaching material isn't the highest quality you've seen. Yeah, I'm pretty sure this is it. But this is the I'm pretty sure this is the formula. Yeah, this is the formula, and this is the formula to understand. And this is just some other stuff that isn't really important. I feel I did forget something though. The entire triangle together, I've explained PV over T. There's also another one, P1 V1 T1 equal to P1 P2 V2 over T2. That is I did this really fast because I'm pretty sure you guys can understand the procedure already. This one is a more complicated procedure, but you guys can pretty much understand. This is called the combined gas law, and that's just something to understand. Now, I'm pretty sure my teaching skills aren't the best, but I do have something else that I want to just touch on because we're almost out of time. And this is just all I believe that I'm gonna do something. I'm gonna touch on something else. So I'm gonna very roughly touch on. Remember the example where I put mass inside water? Well, let's say like now we put like, let's say this is water right here. You guys can tell that's water, and I have a big black mass called I'm gonna call this a 5 kg mass. Let's call this 5 kg, okay? And if this is 5 kg mass, and this is iron, made of iron with a density of 200 and, let me just search up iron density. I truly don't know this. So it's 7874 kg per meter cubed. And water, you already know the density of. What is the buoyant force? Buoyant force, have you ever experienced this when you put your hand inside water, the water tries to force you back? There is a force that comes out of here, and that's just buoyant force. Buoyant force is a simple way to put it, is just the mass of displaced water. So it's not just 5 kg. You cannot assume it's just 5 kg. Because as I've explained earlier, I mean, I haven't explained this yet. I'll explain now. Something I need to explain is that this is in terms of the density of iron. So we need to find it. What about the density of what? What about in the terms of density of water? I'm pretty sure you guys know where I'm going with this. But if you guys just like, you guys can pretty much find the, because what you need to do is that volume. It states volume is something that will always stay the same. It's going to be a constant. So when you put this 5 kg block through to water, it's going to take up that volume. And the volume, if you've figured it out by now, is just 5 kg times, no, not times. Oh, technically, divided by 7874 kg per meter cubed. Now I know what you guys. This is going to be a really small number, but this, if you guys understand this correctly, you guys will see how the units kg cancel out, and because kg cancels out, all this is just you're just left with the meter cubed, and you can find this yourself. We call this x for now. I don't really want to go to the, but this is x for volume, and because you know x for volume, and you know the density of water is 1000 kg per meter cubed. To find the buoyant force, all you have to do is multiply 1000 kg per meter cubed by the volume we have here. Let's say whatever x is, because this is supposed to be x meter cubed, and x meter cubed over 1, same thing. You could just cancel the meter cubed. So you're left with this kg value. So it's just 1000 times x kg value. Now this is just the force in terms of kg, mass of displaced water. But to like actual find the force, because force is equal to, because actually I shouldn't even introduce it yet. It's like basically just means total force is just equal to m. That's not it. Well, yes, basically yes, it is equal to that. Wait, I can't. Okay, I got my. So basically, this is just like gravity. You just need to always multiply this by gravity times 9.8 newtons or 9.8 meters per second squared to get the newtons answer, because all forces are newtons, and then you just get the Newton y newtons. I'm not gonna explain this. I'm not gonna like do the math, but you can get the point. Y newtons. Do you see how it works? It's just the format of units. That's all it. If you look at the units of anything in density lab, anything in circuit lab, and especially in density lab, you'll understand everything perfectly. And I think we're out of time. I just wanted to leave it at Boyne's force here, because I believe that this is something we can start tomorrow. Something we can like build this on somewhat, because this is a very simple approach, but there's many different ways to express Boyne's force. That's what I want to get into, because this is like a very basic method, but there's so many methods. What if this is attached to something? What if this is attached from the ceiling and is put inside, fully submerged inside water? What happens? There's like different scenarios that you need to consider for Boyne's force, and that's just something we can get into later. So I'm going to probably end the meeting here. You guys can leave if you guys want.